We've got a very exciting video for you guys today. We're looking at what you call the Gaussian integral, and we're going to do it the typical way, which is in polar coordinates. So it's the Gaussian integral. It's the integral from 0 to infinity e to the minus x squared with respect to x. It turns out it's actually equal to the square root of pi over 2, which is really cool because, of course, there's no indication that pi would even crop up here, but turns out that it does, so it's super cool. But let's just go straight into it. First thing I'm going to say is you need to have a good understanding of double integrals and how to convert a double integral into polar coordinates. If you don't, check the description. You will see a playlist that takes you through all of that stuff, but otherwise it won't make any sense. Beyond that, let's get straight into it. So what I'm going to do is I'm going to start by saying that I, which is the integral that I'm looking for, is the integral from 0 to infinity of e to the minus x squared dx, just like that. Now, I can also square it, and you'll see why that's useful in a second, because it's very difficult to just evaluate how it is. If I square it, it'll end up being easier. So I squared is just the integral times the integral again. But I'm going to do a slight trick here. I'm going to write it as the integral, like that, no surprise at all. And then, by the way, I'm going to change color for this as well, but you'll see why I do that in a second. I'm going to rewrite it, and instead of using x, I'm going to use y. So I'm going to do the integral from 0 to infinity of e to the minus y squared dy. Turns out it's much nicer to just change the letter. Hopefully no one has an issue with doing this because, of course, the integral is independent of x or y. It doesn't matter what it is. They're both just numbers, and they're both the same number because it doesn't matter whether I use an x, a Y, or a picture of Willem Dafoe. It doesn't matter what symbol that I use. They're both the same. So it's completely fine to do this, but there's a nice trick that comes along for the journey. The reason I've written them in a different color is because I'm now going to do a bunch of manipulation to this, and it's easier to see it in different colors. Okay, so I squared is the following. Integral from 0 to infinity. Fine. Now what I'm going to do is I'm going to put the yellow/orange integral inside of the white one, because remember, each of these integrals is a constant with respect to the other, right? Like y is a constant with respect to x. So I can actually just go, this is integral 0 to infinity e to the minus x squared, and I can squeeze the entire yellow/orange integral in here like this, because it's just a big constant, you know? It's a big constant. Turns out, we're going to show later, it ends up being the square root of pi over 2, more specifically. But you can do that. It's completely fine because it's a constant with respect to x. And then we can keep going with our working out. And actually, by the exact same line of reasoning, what I can now do is I can put this e to the minus x squared term inside of this integral, because with respect to y, x is a constant. So now I've got integral from 0 to infinity, integral from 0 to infinity of e to the minus y squared, and then I can put this e to the minus x squared term inside there, and I've got my dy, and then I've got my dx here. And the whole point of that manipulation is that, voila, we have got a double integral. So I'm just going to ditch the different colors now because it doesn't matter anymore. I'm going to rewrite this as e to the minus x squared plus y squared in brackets like that, and then I'm going to go dx dy. It doesn't matter whether it's dy dx or dx dy. The limits are the same, so it doesn't matter. But hopefully you guys see how I've managed to do that. Now, it might look like we've gone from something relatively simple looking to something that is noticeably harder, but actually, if we convert this thing into polar coordinates, it is going to save us, and it's going to become really nice, because the problem is this is kind of a dead end otherwise, because we literally don't know what this function integrates to with respect to x or y. Notice that actually this has a symmetry where it doesn't matter whether we're looking at x or y. It's a symmetrical function in that way. So it's a dead end either way. We can't do anything. We have to use polar coordinates. So what we do is we do just that. So remember, in polar coordinates, x is r cos theta and y is r sine theta. And dx dy, or dy dx, is r dr d theta, okay? And this extra r term, you're going to see in a second, it saves us. So now we can rewrite I squared as the following. Double integral e to the minus, and of course, because we're in polar coordinates, x is getting replaced by r cos theta, y is getting replaced by r sine theta. When you square them and add them together because of the Pythagorean trig identity, you end up just getting minus r squared up there. And dx dy is r dr d theta. Now we need to look at the limits. So what would the r limits be? Well, I'm doing this very non-rigorously, of course. It's much better normally to like draw the region and actually take limits. It's a bit funny to even have the infinity up there at this point or shortly. So there's a lot of slight hand waving going on. I will be completely clear about that. But it's completely fine. This is the actual way of doing it. But in a casual kind of way, without really justifying it, we can say that r is going from 0 to infinity. So the value of r is going from 0 to infinity. The reason for that is if you very quickly imagine the region that we're integrating over, it's just like it's this entire top right quadrant in the x and y axis, because the x limits are going from 0 to infinity and the y limits are going from 0 to infinity like this. So it's the top right quadrant, and you can see that to get to any point you need r to go from 0 to infinity. Okay, equally theta is going to go from 0 to pi over 2 because that's a 90 degrees. So it's going to go all the way in that top right quadrant as well. So those are our limits. And now you guys can see that actually we have a function that is integrable. We can actually integrate e to the minus r squared times r with respect to r. We absolutely can. So let's do that right now. So rewriting, we've got integral 0 to pi over 2. Now what is this? So r times e to the minus r squared is going to integrate to definitely e to the minus r squared times something. And if you differentiate e to the minus r squared, you will get minus 2r times e to the minus r squared. Now we've just got 1r, so we should probably divide this by minus a half, okay, or times it by minus a half. Now if you differentiate this, there's an extra minus a half here to cancel out the minuses and the 2 and the half and stuff. So that's basically the logic behind why that integrates to that. You could also do reverse chain rule or whatever else that you want to do, but that's basically the logic behind it. And we need to plug our limits in, and we've got d theta there. And our limits are 0 and infinity. And again, really what you need to do is take the limit as something like t approaches infinity. 100% that is worth doing in a real, in like a formal kind of exam or something like that. But right here, we're going to do this very casually. So minus a half times e to the minus infinity squared is going to be 0. Hopefully we can see that if we were to let some variable go to infinity and plug it in, that's what we're going to get. And then we subtract minus a half times e to the 0 there. We've got our d theta. Okay, and hopefully you guys can see that actually now we have conquered it. So we've got pi over 2, and then this is just the number 1/2 d theta. Integrate 1/2, you get theta over 2. And then we can plug our values in, and it looks like we have got pi over 2 divided by 2, which is pi over 4. And of course, that's just like pi over 4 minus 0 over 2, so it's just pi over 4. So what we've found is that not I, but I squared is pi over 4. So I squared is pi over 4. That means that I is the square root of pi over 4, like this. And this can be rewritten as the square root of pi and then divided by 2, like that. And that is the value of this Gaussian integral. So the integral from 0 to infinity of e to the minus x squared dx is indeed the square root of pi over 2. Very cool. One more thing I'm going to add to this is because this function is symmetrical about the y-axis, so that means that it's an even function. You can also say that the integral from minus infinity to infinity of e to the minus x squared dx is just plain old square root of pi. This is the same thing. You don't need any extra working out for that. You're just doubling it because it's the area to the right of the y-axis is the same as the area to the left of the x-axis. So you just double it if you want to go from minus infinity to infinity. And some people even call this version of it the Gaussian integral as well. That's absolutely fine. Either way, they're both known as the Gaussian integral. So that's how you do it. Hopefully that was helpful, guys. And this, by the way, I can't really emphasize enough, this is an incredibly important result, and this result is used in every area of math. So as far as statistics and probability, and of course just like plain old integration and all sorts of like higher level calculus, so things like the gamma function and all that stuff, this is related to it. So it's incredibly important, and this is just one of several ways, as far as I know, of actually doing this. But this is, to me, the most simple and famous way of doing it. As always, guys, thank you for watching, and I'll see you in the next one. Cheers.